Okay, nature is highly organized, and if you don't have all the components, you can't have any organisms. It's kind of like building a house. Okay, we can't have a house unless we have a foundation. On top of the foundation, we have to have the main structural beams, and on and on and on. You need nails. You need to have sheetrock. You need to have all kinds of equipment, all kinds of items, and able to build a house. You have to have a roof, windows, okay? We can't have this house without all of these other components. Well, nature is sort of the same way. It's maybe not the best analogy. However, it's highly organized and there's various levels. And as you go higher and higher amongst the levels, or as you go up the hierarchy, we're going to see that the higher levels contain everything from the previous levels and then some more. And then if we keep adding things, we get more and more complex. So to start this conversation, what we need to do is we need to look at what is the smallest particle around, okay, in our universe that we know of, because that's our starting point. And those particles are called quarks, Q-U-A-R-C-K-S. Okay, it's a quark. And the quarks are kind of a strange thing. They are very unstable. They weren't discovered until the late 70s. And you can see that they have funny names: up quark, down quark, strange quark, charm quark, top and beauty. Okay, so these are little tiny particles, and they in turn, when they're put together, they make up something that you probably are familiar with called the subatomic particles. That is the protons, the neutrons, and the electrons. Okay, so the smallest entity, the smallest thing we know of are the quarks. And the quarks then, when they're assembled, and you see there's different types, will make up subatomic particles, that is protons, neutrons, and electrons. So you can see here, for example, a proton is made up of two up quarks and a down quark. That's a proton, which is positively charged. We find that in atoms. We also find neutrons in the atoms, okay? Neutrons are made up of two down quarks and one up quark, okay? So we just need to understand then that these particles that are called the subatomic particles, the protons, the neutrons, and the electrons, are made up of something even smaller, and these are quarks. Okay, so when we assemble the protons, the neutrons, and the electrons, since the protons are positive and the electrons are negative, and we know that opposites attract, that's really what's going to hold the atom together, the fact that there's positive and negative charges, and that will account for the stability of a neutral atom. So let's take a look. And you can see here we have a proton and we have a neutron. This is what we call the nucleus of the atom. Okay, now there's also a nucleus in a cell, so don't get confused. But this is the nucleus of the atom. It's most of the mass of the atom is localized in the center. And then you see circulating around the outside of the atom, you have the electrons, which are negatively charged. Remember, these particles here, the subatomic particles, are made up of smaller particles called quarks. But in any event, what makes this work and what keeps us as an entity called an atom is the fact that you have the positives pulling on the negatives, and that keeps the whole thing working, okay? So most of the mass is going to be in the center, that's called the nucleus, and the electrons are circulating around the outside. So we've gone from quarks to subatomic particles. When we put the subatomic particles together, then we wind up with the atom. Okay, so here's a nice picture of what's called a helium atom. And you can see that in a helium atom, there's actually two protons and there are two electrons. Okay, atoms are always neutral. So you have two positives and two negatives, and the neutrons are neutral. And you can see then that because of the pluses, okay, you have the attraction towards the electrons, and they stay and they circle around in an orbit. And this makes up what we call a helium atom, okay? So atoms then are made up of protons, neutrons, and electrons. The number of protons determines which atom you have. So for example, if you have one proton, that means you're helium. If you have 2 protons in your nucleus, then that means you are going to be helium. I think I said that wrong. 1 proton is hydrogen, 2 protons is helium. So here's another picture of another atom. Again, we see in the center we have protons and we have neutrons. And then you see this in this particular picture of this atom, there's more than just 1 orbit for the electrons. We can see here that we've got 6 electrons, okay, 6 electrons. So if there's 6 electrons, how many protons do we have to have? We have to have 6, right? Because the charges have to balance. In fact, you count here, 1, 2, 3, 4, 5, 6 protons, 6 electrons, but they're not all in the same orbit. There's 2 in this one, and then further out there's another 4. Okay, these orbits are called shells. Okay, so there's different levels in which we find the electrons as soon as we get past 1 or 2 of them. But you see again the nucleus, and around it we have circulating the electrons. The pluses and the minuses keep this intact. Since this is a atom that has 6 protons, well, what does that tell us? If you've got 6, okay, let me go to my periodic table. So if I have 6 protons, then I'm really talking about carbon, because the number of protons is always, they tell you on a periodic table, they define where the different numbers are. In this particular periodic table, you can see that the atomic number, which stands for the number of protons, okay, is above the symbol. So 6 protons, the one we were looking at just a minute ago, okay, this has got to be carbon, because you've got 6 protons and you've got 6 electrons. And here's again our hydrogen, which we talked about a minute ago. And if you've got 1 proton, you're hydrogen. If you've got here, oh, here's the 6. It is shown in this picture too. 6 protons, you are carbon. Okay, and then you can take a look at some of the other ones. If you've got 8 protons, you're oxygen. Okay, you can't have 8 protons and be anything but oxygen. Okay, the number of protons defines which atom you are. Okay, if you have 7 protons, you're nitrogen. And you can see some different examples of the atoms that are here. Now, the atoms are arranged. Several atoms make up the elements. And here is the periodic table of elements. And it's arranged according to increasing atomic numbers. In other words, we start out with 1 proton for hydrogen. Then we go over here, 2 protons for helium, 3 for lithium, 4 for beryllium, and you see the numbers are increasing as we go back and forth across the different rows of the periodic table. So it's not a haphazard arrangement, the periodic table. It's very organized, and it's done according to the atomic number by increasing atomic numbers. So you see down here, for example, you have an element called I'm not really sure of the name of this one because they've switched over to Latin, but number 114 is 114 protons in, I think this is called uniquatium, but there's 114 of them in this one. So you can see if we can get quite large numbers of protons. And some common things, you know, oxygen has 8 protons, and you see here some other things. Neon has 10 protons, and so forth, okay? All right, now, if you take atoms, okay, and you hook them together, what do we do next? What is the next level of organization, okay? So, for example, if I take 2 hydrogen atoms and I chemically bond those with an oxygen, I form something called water. And actually, water, what's keeping this molecule together is the fact that the electrons of the hydrogen and the electrons of the oxygen are interacting, and that's what forms the chemical bonds that holds them together. Okay, so when you have more than 1 atom, we then go to the next level of organization, which are the molecules, okay, or compounds. They bind together. Here's another picture. This is a ball and stick model. This is a more of a spatial representation. These are spatial representations. They draw this like this to show you the how large the orbital area is for the electrons that are around the oxygen. So you get a better idea of the size of the oxygen in this picture, whereas this one's just showing you what's involved in water, 2 hydrogens and 1 oxygen. Here's another example of another molecule. If we have 1 carbon and it is hooked up with 4 hydrogens, then we have something called methane, CH4. So carbon's pretty large, okay? And you see then when it's hooked up to 4 hydrogens, you form the compound called methane, okay? And atoms are going to be bound together. I mean, these little sticks represent the bonds. They're bound together in 2 different types of manners. One is where the electrons between the different atoms, they can either be shared between the atoms, or they can be transferred. And then one becomes positive and one becomes negative, and then that will hold the atoms together. But I don't want to get into the bonding characteristics, but just to say that there are different types of bonds that hold atoms together. So the electrons are either going to be shared amongst themselves between the different atoms, or they get transferred from one atom to the other. And then you have what are called ionic compounds, but let's leave that out for now. And here's an example of an ionic compound, sodium chloride. Sodium chloride is actually made up of, sodium actually donates all of its electrons over to chlorine. So sodium then becomes positive, chlorine becomes negative. This is an ionic compound. So you form a positive and a negative, and that's what holds all these atoms together in this crystal lattice structure. Okay, so it's a different type of bond than these over here. These bonds that we've looked at with the water and the methane, these are covalent bonds because the electrons are going to be shared. But over here, you have a transfer of electrons from one atom to the other. Therefore, one's positive, one's negative, and that electrostatic force holds all of these ions together to form our sodium chloride, which is none other than table salt. So this is an ionic compound, okay? Okay, so we've gone from the atoms to the molecules or compounds, okay? Now, we have some other types of compounds that are a little more complex, and one of these is glucose. And the reason I want to talk about this is because I want to introduce now the 3 or 4 very important biological molecules, okay? And to do that, we want to look first at glucose. Glucose is another molecule, but you can see here, it's more complex than anything we've examined so far. You see, but there is a hexagon type of ring structure with an oxygen in there, and you see that there's branches, on top and bottom, and so it's pretty complex. When you draw pictures like this in chemistry, it's assumed that at every one of these apexes, there is going to be a carbon atom. Okay, and we're getting into more and more complex compounds at this point, so we're going to stop here. But so far, we've understood that the quarks make up the subatomic particles. The subatomic particles make up the atoms, and then atoms make up molecules. We've looked at some simple types of molecules, water, methane, sodium chloride, and we want to go on to the more complex, okay?